Interest of time, let's get started, Andre. So I want to quickly introduce you, and then we can get started with the seminar. For everybody who is on the call on the Zoom, thanks for joining in for our seminar series. I know it's a very different seminar series this year. We are also introducing to our own graduate students, to our faculty, what internally we are doing in research among ourselves. It's a better way to know each other a little bit better during this time. Dr. Andre Mazzoleni is an associate professor in our department. He's been in the department since 2004. Prior to that, he was at Texas Christian University for about 11 years. He's actually got his BS from Duke right here across town. And then he did all his graduate work at University of Wisconsin-Madison. Dr. Mazzoleni started off doing a lot of space-related work, and that's where his real prominence in research was for a long time. But he has pivoted into some interesting multidisciplinary research in the last few years, and with the same kind of knowledge that he has in doing space, he's doing some renewable energy. He's going to share all that. So, Andre, take it away.
Okay, thank you, Srinath, and thanks everybody for joining this seminar today. So I want to start by giving just kind of an overview of the Engineering Mechanics and Space Systems Lab. When Srinath asked me to give a talk kind of about the research going on in the lab, I kind of tried to decide how I wanted to structure this. So I decided to kind of group this around multi-body dynamics. We also do some solid mechanics work as well. You can kind of see here in the middle here, we do some finite element analysis of the spine, but wanted to kind of focus on the multi-body dynamics. And so rather than pick just one, do is cover a number of topics that I've been working on in kind of the space arena, and then show how they all kind of prepared the lab to work on this really exciting new renewable energy project. So I'm going to be talking about tethers in space, and then bio-inspired robotics for exploration of Mars, balloon trajectory systems, and then it's going to end the talk talking about some of these renewable energy projects that we've been working on. I can see the lab has over the years been funded by NASA, the Coastal Studies Institute, Department of Energy, DARPA, and then some spine equipment manufacturers have given us the money to work with a local spine surgeon on doing some finite element analysis of the spine. So I wanted to give you a little bit of the current students in the lab. Currently we have 8 PhD students and 3 master's students and 2 undergraduates. And I've also included 3 recent alumni that graduated in May because they actually contributed quite a bit to the work you're going to see here today. And I apologize in advance if I've inadvertently left anybody off the list here. So just kind of a brief outline of the talk. I want to go over just a kind of a brief introduction to multi-body dynamics. Then we're basically going to start in space with space tethers. Then we're going to move into the upper atmosphere and talk about trajectory control systems for scientific balloons. Then we're going to move down to the ground and look at bio-inspired rovers for surface exploration. And then we'll finally end up in the sea. So we're going to go space, air, earth, or ground, and then sea. That'll be kind of the trajectory. And I'll spend about half the talk on these first 3 topics, and the last half of the talk will be on kind of the renewable energy. Before I start those, I did want to just mention that we do have an effort going on in modeling of the human spine and surgical instrumentation of these long surgical contracts, trying to figure out ways we can help use finite element analysis to help surgeons have their patients avoid situations where the rods that are used to say straighten up some spine break. So that's a topic really for another talk, but I wanted at least to mention that we do that work here. Okay, so let's talk a little bit about multi-body dynamics. And here's this is kind of a renewable energy system. We have a bunch of coaxial turbines here that are extracting energy from the Gulf Stream. And if you look at this diagram here, you can see you've got a lot of things going on. You have a multi-body problem. You have these 3 bodies here that are moving the shaft here, and then the 2 rotors at the end. There's actually also a generator in here. And then you have this flexible tether here. So this kind of, encompasses, a lot of what you're going to see in a multi-body dynamics problem. Now, what are the methods we use in multi-body dynamics? There's three primary methods. There's actually probably a dozen total that people use, but most of the people use either Newton-Euler methods, Euler-Lagrange methods, or Keynes equations. Our lab is a little bit unique in that we use all three on a regular basis. A lot of labs basically just kind of pick one of these and work with it. It turns out that they're, depending on the problem, one of these can often be superior to the other two. In terms of kinematics and methods, there's two ways to do kinematics. One is with Euler angles and one is with Euler parameters or quaternions. They're actually, when people say quaternions, most people when they say quaternions are actually using Euler parameters. That's a discussion for another day. And there's pluses and minuses to either one of these. It kind of depends on the problem, which one of these you want to use. Now, what are the tools we use in multi-body dynamic simulations? Well, we use MATLAB and Mathematica a lot for initial work. Sometimes we can use that for all of the work. If we're running lots and lots of cases and the cases take a long time to run, then we may port the code over to C++ or Fortran. And then one of the things we do a lot of in the lab is build prototypes to kind of do a reality check on our system. So, for example, we might be doing analysis of a very large system that would cost millions of dollars to build, but we can build a small version in the lab, apply our code to that system, and see if the results we get from doing experiments with the small scale prototype match the code. And of course, we use inertial measurement units and high-speed cameras to take the data. Now, what are the challenges of multi-body dynamics as opposed to a single body? So if you pick up a typical textbook on advanced dynamics, they'll spend a lot of time talking about a single rigid body, has 6 degrees of freedom, and they'll derive Euler's equations of motion and so forth. But really what all the challenges start to really crop up when you have more than one body involved in the system. And so let me just kind of go through that very briefly here. You obviously have the kinematics of keeping track of multiple bodies in the system. How do you properly model the external forces acting on the system? So, for example, this system here, you have this whole body may be pitching and rolling in the ocean due to the currents, and then these rotors are spinning. So how do you actually calculate the forces that the water is exerting on that system is very, very challenging. Then there's properly modeling the interaction forces between all the elements of the system, internal frictions and so forth, and contact forces. And when I review papers, multi-body dynamics papers, usually if whoever's doing the work is not a specialist in multi-body dynamics, they often make mistakes here at this portion. They don't properly model the interaction forces. Then how do you handle the constraints? You have both holonomic and non-holonomic constraints that you have to handle properly. And then you have systems where you have time-varying moments of inertia because the different elements of the system are moving around, or you might be losing mass or gaining mass if you have propellant, or you're taking on water to change the ballast of your system. And I've actually read papers where they'll take just Euler's equations of motion and they'll just put in time-dependent moments of inertia and integrate the equations. And it turns out that's a completely wrong way to do that. It's much more complicated than that because the Euler's equations of motion are derived for constant mass systems. And then how do you discretize the continuous or elastic elements of your system? So how do you take this continuous long flexible tether and break it up into a set of kind of discrete elements that you can actually combine with the rest of your model? And then often you have to sum moments about points that are not the center of mass of the system. That introduces a lot of complexity, but you often have to do that because your forces actually and your moments are often most easily calculated about a point that's not necessarily the center of mass of the system. Then of course there's how do you choose the proper level of complexity for your system? So if you model everything to the nth degree, you'll end up with a model that would take 3 months to run a single case. So you have to simplify the system, but you can't simplify it too much. So what's the appropriate level of complexity for your problem? And then of course, once you're running your code, there's all sorts of coding and numerical issues you have to deal with in terms of what kind of integrator do you want to work with and so forth. Okay, so that's kind of a, just in a nutshell, the type of things that go on when you're studying multi-body dynamics. And then just to remind you of kind of the outline of the talk. Okay, so let's go ahead and start in space here. I've done a lot of work on space tethers. There's some pictures of some experiments here, date always back to the 60s. NASA spent about $1 billion on tethers in space in the 1990s and then into the 2000s. Although they've now, more of their budget has been devoted toward the, the new space launch system. But there's a lot of things you can do with space tethers, from artificial gravity, reboosting the space station, deorbiting satellites, interferometry, and so forth. But what I'm going to focus on here is some work we did where we looked at asteroid diversion. Okay, so and most of the work here was done by a student who was on an Air Force fellowship. He came here to get his PhD, David French, and he did some really, really nice nice work. And I'm going to be presenting you a lot of the work that we did when he was here. Okay, so let me talk a little bit about just what a NEO is. It's a near-Earth object. It could be an asteroid, could be a comet. They're sometimes called PHAs, or potentially hazardous asteroids. But I want to show you just a couple of reasons why people are concerned about near-Earth objects. So as anybody who likes dinosaurs know, the Chicxulub crater, about 65 million years ago, there was it's believed that a large asteroid struck here in the Yucatan Peninsula. You can see kind of the satellite image there of the crater, and it basically caused worldwide species extinction. But on a more recent event, I think this happened in 1908, the Tunguska event. There was a massive event. It could have been an asteroid, it could have been a comet burst, happened over Siberia, and it just devastated a whole region. But fortunately, it was an extremely lightly populated area, so really, it had very little impact. But I want to show you here. This is a picture here of New York City, and if we overlay the Tunguska event on top of that, you can see that had this event happened over New York City, you probably would have lost, and that's in fairly recent history. So fast forward to 2004, NASA came out and said that there was a 1 in 37 chance that an asteroid was going to strike the Earth in April 2029. Kind of got people's attention. The next day they came out and said, oh, we made a calculation error. It's only 1 in 45,000. So people kind of were able to breathe a sigh of relief there. But it did, it did kind of reanimate efforts to plan for mitigation. And basically, NASA did two things. One, they started using satellites and developing satellite systems to try to detect, potentially threatening near-Earth objects. And they also started looking at mitigation techniques. So some of the techniques, and I want to show you these just because they're all what I would call extremely challenging and you could almost say far-fetched. And I want to show you these just because ours is probably equally challenging, but I want to show you that it's really kind of in the same neighborhood in terms of difficulty. So everyone talks about blowing up an asteroid. Well, you can't really blow up an asteroid, but what you can do is detonate a nuclear device near the surface. It creates a shock wave then, which takes part of the asteroid. The pieces will explode and break off and travel in one direction. And so you'll get a reaction force on the asteroid, which can change its orbit. Then some people should say, well, let's find an asteroid that's going the other direction and somehow steer it so the two of them hit each other and collide. You can land on the asteroid, try to despin it, and then fire a rocket engine to kind of gently push it off course. You can use a gravity tug where you orbit a large satellite nearby and use the gravitational force between them to kind of gently tug it off course. You can actually, some people say, well, you should paint half of it with some kind of thermal coating so that you have an uneven thermal emission from it, and that would then change the radiation. That's something called the Yarkovsky effect. And I'm not a thermodynamicist, so I can't really talk too much about how well that would work. And then our technique is to use a long tether and ballast. Okay, so here you have the situation. So here, basically, you have an asteroid with an Earth-crossing orbit. And the idea is you don't want Earth and the asteroid to arrive at the intersection of those two orbits. So what you want to do is somehow change, if you know that in 5 years, 10 years, whatever, this asteroid is going to be hitting the Earth, they're both going to be here at the same time, you want to somehow alter the trajectory of the asteroid so that doesn't happen. And so what we've been proposing to do is you basically attach with a tether a long ballast mass. It could be you know, a spent booster rocket. We've been looking at masses on the order of about a Saturn V rocket to a long tether here. And what you do is you change the center of mass of the system here. So now it changes the orbit. And when you change the orbit, then hopefully now instead of this asteroid hitting the Earth here, it's actually either moving slower or faster at that point. So it's actually missed. Well, actually, I should just say that the orbit has been changed such that they don't arrive at the same time anymore. Okay, well, here's the mathematical model that looks like it. You can see we have the tether model over here. That involves the interaction. We've broken this up into several nodes, and this is a theme you'll see throughout the talk. I've just kind of put here's the tether equations, and here are some of the orbital mechanics equations. But I want to go through here and then look at some of the results of that. So here what you can see is this is a plot over time of the distance between the asteroid and the Earth. And you see as they move around their respective orbits, the asteroid gets closer and farther away from the Earth. And down here you can see it actually hits. Now, by adding the tether and ballast here, the plot looks almost the same, but it's enough of a difference so that when you come down here after 10 years, you actually miss the Earth by about 21 Earth radii. The scale here is 10 to the 8 kilometers on this y-axis here. And actually, NASA actually defines a successful mission to be if you miss the Earth by 1 Earth radii. So the next thing we did was we did a bunch of parametric studies. So we wanted to see if you take a look at the mass ratio between the ballast mass and the asteroid, you look at the length of the tether you use, you look at the semi-major axis of the asteroid and its eccentricity, and we do a detailed parametric plot here of how much of a miss distance would you get. And this particular plot is for after 20 years. And you can see over here you're getting a miss distance of about 100 Earth radii or so. But let me show you a little easier to understand plot. This is a plot of all the known asteroids that have Earth-crossing orbits. And on this axis, we have the mass, and this we have the tether length. And basically, we're showing which one of these asteroids can be diverted by a given length. So you see that if you have a tether length of about 100,000 kilometers, which is, that's basically the length of the proposed space elevator that NASA's been looking at, you can see you can actually divert about half of the known Earth-threatening asteroids. Okay, so just want to say, basically, we've added a method to the arsenal of things that people are looking at. Hopefully, we won't have to actually consider this for real for hundreds or thousands or millions of years. But you said we had an event like this just 100 years ago. So, and we got about a dozen publications out of this work. Okay, so the next thing I want to go through, and I'm going to go through this very, very, very quickly, and I apologize to the students involved, but I want to make sure I have plenty of time to talk about the renewable energy. This is the trajectory control system for scientific balloons, and kind of the lead people on this is Saurabh Agrawal, who's a master's student, be finishing up this fall. Chris Yoder, who's a PhD student, will be finishing up this year. He's currently a Pathways intern at NASA's Balloon Programs Office, and he's actually working on this problem for NASA at NASA. And then we have Garrett Moats, who just graduated this past spring, and he's actually now working on renewable energy for Sandia. And I just want to show you a picture here, scientific ballooning. Just show you this picture here. This is a typical payload, and here's a person here, just to give you the idea of the size of these things. So what NASA is worried about, they don't want any of these balloons passing over a populated area, because you can imagine if you had a failure and if something that massive fell in the middle of a city, it would be just a disaster. So what they want to do is, for example, here's an unguided path of the balloon that goes over a populated area over South America. They would much rather be able to guide it so it goes over a much more lightly populated area. And there are three ways that they're looking at doing that. One is you can actually lower and raise your altitude by inflating and deflating your balloon, and then you catch various air currents to move around. Then you could attach a propeller and a propeller system, or you could do a long tether and a sail. And they all have strengths and weaknesses. The propeller isn't going to work very well at high altitudes. The altitude modulating system, you have to count on having the appropriate wind speeds where you at the altitude you need them. Now the long tether and sail here, the way it works is you suspend this tether in this airfoil as maybe a 10-kilometer long tether. The whole system is basically going to move at the speed of the balloon. The wind speed down here in the denser atmosphere is going to be different. So you're dragging this airfoil through the atmosphere. Since it's at 90 degrees to a traditional airfoil like on an airplane, your lift generated will be sideways, and you can use that to actually control the trajectory of your balloon. Okay, so we created a dynamic model of the system. You can see over here, here's our tether model. I want to point out, Tom Gemmer also helped us out, and Raj Wagela from the Applied Aerodynamics group, Dr. G's lab at NC State, also helped out with the dynamic model. We did, let me see if I have the test. Yes, we did some, I took the slide out. We also did some experimental work here, and I know that Maria Ailman also from Dr. G's lab helped out with that as well. The field test here took an army of people, and we have a very collegial lab, and these are all people from the Engineering Mechanics and Space Systems lab that went out to help with these field tests, where we actually tested out this wing system to find out what kind of a force could we actually generate on the balloon and to try to validate our models. Very simply, we've done modeling results, we've done experimental work, so far it looks like the model and the experiments agree, and we have about 6 publications to date on this. And what remains to be done is to compare the 3 methods. So we now have, NASA already had models for these 2 systems. Now we have a model for the tether sail. And so Chris is currently working on that, and we'll wrap that up this year. Okay, so now I want to move on to bio-inspired rovers. We've been in space, we've been in the air. So I want to talk about applying multi-body dynamics analysis to ground-based systems. Here's a traditional rover. It's Mars rover, extremely capable, but it really requires very, very flat terrain in order to operate. Here's the interesting areas of Mars where you might find water and so forth. A traditional rover is going to have a lot of difficulty traversing these terrains. It's probably going to tip over once you get above about 15 degrees. So can we take inspiration from nature? So here you can see a tumbleweed rover that's windblown, and here you have animals that can travel with 4 feet here or 8 legs, or they can also curl up into a ball. And so we wanted to use these for inspiration. So first thing we looked at was tumbleweed rovers, and we've looked at these for quite a while. Here are just some of the students who have worked on this project. Here you can see we tested some prototypes. Here's a NASA prototype they tested on at Antarctica. But I want to show you now some of the modeling work we did. We used Keynes equations for this model. Now, one of the things is that these rovers are going to be moving through rock fields. So that was a very important part of the modeling effort. So what we did was we looked at the Viking data to get the kind of a distribution of the rock sizes, what the rock sizes are and how they were distributed throughout throughout Mars. And then we generated we would generate random rock fields so that we could do Monte Carlo studies. Here you can see a rover moving through this system. We actually generated the rock field. We stopped the simulation every few seconds and then generated a new rock field around where the rover was. That's in order so you don't have to generate the entire field every time. Here you can see we did some experiments where we validated our model with rolling some spheres down through a simulated rock field, and we compared those to validate our model. Here are some of the results. Here you can see these are Monte Carlo simulations of rovers of various diameters and masses, and this is how far downrange they traveled after about 8 minutes. So you can see here the rover with a radius of 3 meters and 20 kilograms didn't move nearly as far as the radius at 5 meters and 40 kilograms. And you will notice that some of them actually got stuck near the beginning of the simulation. They end up being wedged between 2 large rocks. So these are the type of studies you can do with a model like this. And these are just some looking at the average downrange position as a function of doing these Monte Carlo studies. You can see these error bars here because of the fact that we did multiple studies. And what we'd like to do now is we don't want these things just to be blown by the wind and go wherever the wind takes them. We'd like to be able to control them. So what we've been doing is looking at, can we, by moving masses around inside the structure, and here's one obviously without the sails on it, can we, by changing the center mass dynamically, can we actually steer this thing? And here's a simulated rover. Here you can see you're kind of going and steering around some of these, craters and hills and so forth. And we have Ashwin and Sri Chakra have been building this model here and are currently working on that. Okay, so let's move on to the Transforming Roving Rolling Explorer, or T-Rex. This is one based really on the golden wheel spider, which is a spider that crawls along ridges on sand dunes. If it sees a predator, it curls up into a ball, actually more like a wheel, and rolls down the hill. And then it stops and then goes about its business on 8 legs. And so you can see here we wanted to build a rover to do the same thing. The rover can move around on nice flat areas. If it wants to travel down rough terrain, like for example a hill, or down into a crater, it can transform into a ball, roll down the hill, and then it can go ahead and transform back into a traditional rover. Now, one thing we'd like to be able to do is control the rolling motion. And one way you can do that is, since you have these 8 panels that are folding up anyway to form the ball, can we partially fold out those panels and change the center mass of the rover and therefore change its direction? And so here's the dynamic model here. This is Rob Parsons, this is Lionel Edwin who did most of the modeling on this. You can see here the relationships between torque and angular momentum. Here you can see all the extra terms you get when you differentiate the angular momentum beyond what you get with Euler's equations, because of the fact that you have, basically in this system you have 9 bodies moving around. Here you have our Euler parameter, kinematics, and so forth. And so one of the things you can do with a model like this is do some parametric studies. So we looked at 3 different chassis sizes, and we also added some masses at the end here to kind of increase the moment of inertia. And so we looked at 3 different chassis and then 3 different mass sizes at the end. So a total of 9 parameters. And we also looked at 6 different terrains. So terrain 3, I think, is very loose, sandy soil, and terrain 4, for example, is kind of hard, rocky terrain, and then everything kind of in between there. And let me just show you a video of what this looks like. So this would be, we're trying to see with this rover, if we had to move up a slight slope in order to get to the edge of a crater to go down to the crater. And you can see that this rover here design does quite well. But let me show you one where it doesn't work. Here's one where the rover stalls. So you can see the panel opens up, it rolls forward a little bit, the next panels open up to try to move it forward, and you can see then that it basically stalls out. And then here's one where the soil is just too slippery for the given slope, and you can see it basically just keeps slipping. Okay, so we wanted to see what's the ability to scale inclines, and basically we said we have a successful climb if every time the rover spins once about its own axis, it climbed at least 25% of what its circumference is. So you take basically the 2 pi r, and if every time it turns around once, it's gone at least 25% of 2 pi r, we consider that to be a successful climb. And what you can see here is we looked at the maximum slope that you could climb for all the various rover parameters over the 6 different terrains. So this is the type of thing you can do with this. Here I want to show you just a we did a simulation here where you can show by the rover, if it wants to avoid these obstacles here, it can do this by strategically opening and closing its panels. So you can see it, at least in simulation here, it does quite well. Okay, so the next thing we wanted to do, and we just recently started this actually, and this is work that, kind of we were able to do some testing before COVID shut everything down in the spring. But here you can see we've actually built this the prototype here. You can see the inside of it with the motors and the microcontrollers and so forth. Here you can see what the kind of the rack and pinion system to open the panels. Here are some of the electronics. Here's an animation of the rover undergoing a, basically it's going to undergo a right turn. When it gets to the next dot, you'll see it'll kind of go a right turn there. Okay, now here's a simulation here. This is not a simulation, this is the actual prototype, and you can see here it is executing that right turn. And that's an EV3, I think, at about midnight, I think. We want to pick a time when it was rather quiet. And then here's just some data from the turning test. Here, the blue and the black lines there. This is actually a left turn. You can see that the simulation and the prototype actually agreed quite well. Okay, so between the rover, the tumbleweed, and the T-Rex work, we've got about a dozen publications out of that. We're also looking at some Earth applications of all these technologies. The NSF just started a new program called Foundational Research in Robotics. So we're looking at this, and also some rovers we've been looking at that can also be amphibious, doing things like landmine detection and scouting, disaster relief, and then exploring the Arctic, because they have a very rugged terrain. You need to be able to move on ice and sand and in water and so forth, and even beneath the water. So we're currently preparing a proposal now to go to this brand new NSF program. Okay, so let's move on now. I'll spend about the last 20 minutes of the talk talking about renewable energy in the Gulf Stream, and you'll see that all the techniques we used to look at this, basically, we already had expertise in the lab because of those other three research areas that we've been working on. Here you can see the Gulf Stream here, this high speed flow here goes past, in red here, goes past the coast of North Carolina. A great source of energy, gigawatts of power. However, where that velocity is, that high speed flow is 1 to 2 meters per second, you can see it's about 3,000 meters deep there. And for scale, this is the new World Trade Center. You can see it down here. So you can see just the challenge. There's no way you could build a tower turbine system to put the turbines up here in the top. So the solution is to have a tethered system. So let's take a look here at some of the solutions. And I know this is a very busy slide here, but we've got a very large effort in this area going on at NC State. So I want to spend a little bit of time talking about that. So it actually kind of dates back to when Dr. Vermillion was still at UNC Charlotte. And we'd both been doing some work for Coastal Studies Institute on different projects. And Mike Mulia at the Coastal Studies Institute contacted us and said he had an idea to actually tether a system in a turbine system in the Gulf Stream that could collect energy by being collected to a tether. And then the idea is to store it with batteries and then drive to the shore, offload the energy, and drive back. So we spent about a year working on that. It turns out that you just spend too much energy going back and forth to make this practical. But it kind of, we learned some really good things there. And this ended up leading to, when Dr. Vermillion came here, we submitted a proposal to the Department of Energy, along with University of Maryland and Florida Atlantic, and also with Dr. Granlund's lab was involved. And this kite-based system here for extracting energy that you heard a lot about 2 weeks ago in Dr. Vermillion's talk. Now, about the same time that this project was going on, our lab was working with Dr. Granlund's lab and Dr. Bryant's lab on another project which looked at coaxial turbines in the Gulf Stream to collect energy. And then after this DOE project came along, we actually kind of, all 5 of these groups joined forces, Dr. Vermillion's lab, my lab, and Coastal Studies Institute with Mike Mulia. There's a DARPA project where they want to use this kite-based system to be able to recharge submersibles that are operating, in the ocean. And so that was funded by DARPA. So we've got a lot of different labs working, 4 different labs here at NC State. We have Coastal Studies Institute, Department of Energy, and DARPA all working on these projects. Now, I'm going to focus the rest of the talk mostly on this project here. I'm going to talk a little bit about the DARPA project and the DOE project, but very little, because otherwise we'd be here for about 2 hours. These are 4 PhD students I have working on this. Sumedh is working on an optimal kite design. Joey is working on a tether deployment and reel-in modeling. Ashwin just joined the group. He's going to be working on pool-based and open water tow testing. This is, I should mention, Sept is also working with Dr. Vermillion student Kartik on the design optimization tools for the kite. Joey is working on reel-in dynamics for the DARPA project, but also obviously has application here for the DOE project. And here you can just see kind of what one of those simulations look like. This is just an animation of some of the simulation work. You see what happens is every time the last link is the one that shortens in this tether model, and then once the link gets close enough, it disappears and we rediscretize the system. Okay, so now let's talk about tethered coaxial turbines for about 15 minutes or so. Here you can see a lot of the people, the graduate students who worked on this project. Here again, we talked about, this is not practical to have a turbine in 3,000 meters of water. So you have to have a tethered system. A single tether is not going to work. I mean, a single turbine is not going to work because you don't balance the torque. You have to have two contra-rotating systems to work. And there's two ways you can do that. You can do it with a parallel plane configuration or with a coaxial system. And it turns out that there are some real advantages to having a coaxial system, which we'll talk about. Now, when you have a coaxial system, obviously you have zero reaction torque, but there's some other benefits to this. One, you have these counter-rotating turbines. So what that means is downstream of the system, you're going to have much less flow disturbance, which is good for marine life, and also will help you if you have a whole farm of these. There's also some, we found that actually with this system here, as you move back and forth, if you might, bob back and forth in the water, there's much less change in the energy generated with this system than with the coaxial than with the parallel system. And you can see one of the interesting things when you have this inclined or skewed rotor system is you have fresh flow that actually reaches the back rotor here, and that's can help improve your energy generation. Also, because you have this uneven forces on the front and back rotor, you can actually use that to dictate the depth and the position of the system, which is really fascinating. Now, I'm not going to go into this chart much. Deepak, his student, was kind of the lead on developing this model. Rodney and Punag from my lab and Punag from Dr. Bryant's lab also contributed. But basically what this chart shows, and I refer you to the paper for the details, is that basically between about 60 and 80 degrees of skew, where 90 degrees means you're actually headed directly into the flow, you have very little change in the coefficient of power. So it's very interesting there. One of the things we did there is we did some testing, and one of Dr. Granon's students, Kelsey, worked with Punag and Rodney on this. So we built a system experimental apparatus that we tested in Dr. Granon's water tunnel. And what we were able to do was to actually validate Deepak's model there. And there's a paper that just came out on that. Okay, so now let's talk about tethered turbine dynamics. Complicated system, you have 3 rigid bodies here in this elastic tether, about 8 degrees of freedom. Here's what the dynamical equations look like. This doesn't even have the kinematics on it, but you can see you have relationships between the torques and the angular momentum and the forces and the accelerations and so forth, and you have the forces acting on the turbines as well there. Now, the key thing with this challenge with this project is calculating the forces acting on the blades. And let me just kind of go back to the picture here. If I can find so as this is moving around and so forth, and these blades are spinning, obviously the flow, if the flow is going from left to right here, the angle of attack and the velocity of the flow as it passes over these blades is going to be affected by the fact that this is skewed, and some of the blades are going into the flow and some are going away from the flow. So this introduces a wide variation in what the forces are acting on this turbine that you don't have if you're just looking at like a traditional fixed wind turbine, for example. So let me get back to where that would be. Okay, and this picture here basically kind of explains that. So you have an advancing or retreating component of the relative velocity that affects the angle of attack and the relative speed over the wings, and that's going to cause all sorts of things. We're using the same tether model basically as we did to the balloon, so we were able to transfer a lot of the balloon work directly into this project, which was very, very useful. We were also able to use a lot of the multi-body dynamics work that we developed for the T-Rex actually went into the dynamic model here. So there was a lot of synergy there between these different projects. We do have a generator in the model. I just wanted to point that out. So it's a fully operational system that we're simulating here. Okay, and let me just show you here a brief video. This is actually, this is simulation of actual data here. And you can see the rotor speeds, they spin at different rates, and this moves around. Eventually this will come to an equilibrium. And that's one of the things we wanted to study. All right, here just as a very early test we did, you can see here's the simulation. And then this is simulating a system that we tested in Dr. Bryant's wind tunnel. If I get this to play, there you go. You see it's kind of, after a little bit of a rough start, it kind of goes, and then it kind of settles into equilibrium. If we look here, you can see that the actual system did exactly the same thing. So this is, as I said, this is very early on, kind of we were impressed by the stability, but also we were impressed with the fact that qualitatively, at least, this model seemed to be capturing what was going on there. Okay, so let's talk a little bit about hydrostatic equilibrium. So if you just don't have, if you have no flow at all, and you put this thing in the ocean, it's eventually the buoyancy is going to, these things are going to be positively buoyant because the tether breaks, we want them to float to the surface. You can see that it would float to the surface and assume a certain position here. And you can analytically calculate what that position is. And so what I'm about to follow, we're actually using a utility baseline configuration that's 18 meters in diameter. And just for scale, the NBA playoffs are going on right now, so I picked a basketball player here. You can see the size of these things; they're just enormous. But we use all the mass and the dimensions and everything for this utility scale. And what we did was we looked at the dynamic model. We disturbed the system, let it float around the water, and come to equilibrium. And we compared that with the analytical results. What you can see is these dots here are the results of the dynamic simulation. The bars here just indicate the kind of the oscillation it went through before it settled down to steady state. And they agreed. So that's at least a validation. It's not the validation we ultimately need, which is an experiment, but it at least gave us confidence that we're getting sensible numbers. Okay, the next thing we wanted to look at was hydrodynamic equilibrium. So we want to just put these turbines in the water with various designs, let them spin up and then come to equilibrium and see what happens. And again, you can see here, we did exactly that. You can see it kind of moves around. These things actually can take several hours, to finally come to an equilibrium. And that's not on the, I mean, computer simulation take hours, but it's actual hours of ocean time. And again, just reiterating, it's the dynamic equilibrium, and you actually have flow, is going to be much more complicated than the static equilibrium because of the fact that you have these retreating and advancing blades, which change your forces. Okay, and that's just repeating that same thing. Now the question is, can we use this dynamic simulation to find out by looking at where these turbines go? Because we found that they actually, depending on the design of your turbine, you're actually going to end up in different drift locations, which is a kind of the left-right horizontal position, and depths. So we want to see, can we use that to actually design a turbine farm where they could all be attached to the same point? And these might be actually attached to an offshore wind farm, for example. So you can collect energy from the ocean while you're collecting energy from the wind. Okay, now I'm going to try this. I'm going to try to show you a video here. So I'm going to kind of exit out of this. And okay, so hopefully you can see that. And you can notice here, notice that these rotors actually, I'm going to replay that. They kind of start in the middle, and as the flow goes, they actually move to 3 different positions. This is a top view. And all we did here, the flow is going from the bottom of the screen to the top screen, all 3 of these cases. But just by appropriately designing the twist of the blades and the location of the center of mass and all sorts of things, you can actually, our simulations anyway, indicate that you can actually drive these to very particular locations, which we thought was really, really interesting. Okay, so now I'm going to go back to presentation. I think I have to, there we go, okay. All right, now what you'll notice here is when we did a bunch of simulations and we move along this curve here, we're actually changing the location of the center of mass. The pitch and yaw of the rotor are actually related, and that's going to be important. Also, this shows that the depth is related to the pitch, as we move along this curve, we're changing the location of the center of mass of the system by just moving a ballast mass around. And the drift, which is the left-right, also depends on the yaw angle. And we know that the depth, the pitch and the yaw are also related. So you got pitch and yaw and center of mass and the relative density, which is the one would be neutrally buoyant and 0.95 would be positively buoyant, because you actually, the turbine system itself would be hollow, somewhat hollow. So you actually have lower density than the water. So by adjusting those 4 parameters plus things like the pitch diameter, the actually control where these things end up. Here you can see some plots that show, I'm going to focus on this one. This is the normalized center of mass location. 0 would be into dead center, and then 10% would be toward the aft rotor. And you can see you can actually affect the pitch angle and the yaw angle by changing the center of mass. And so just to kind of go again, talk about why this is. So what happens is when you have these blades moving, you know, the flow going from left to right here, you're actually going to have, since some of the blades are retreating and some are advancing, you're going to have different forces on the left and right side of the rotor. Now, since this is counter-rotating here, it's going to be the opposite on the back rotor. But if the magnitude of these yaw moments that are induced are not the same, you're actually going to get a net yaw. So once you can actually, and then once you have a net yaw, the thrust from the flow acting on the rotor is going to drive it either to the left or the right. Same thing happens with pitch. Once you, well, actually with the pitch, what happens is if you unbalance center of mass, you pitch up, and then what happens is the net force between the tether and the flow actually drives the rotor down. So these things are actually positively buoyant, and yet because of the tether, they actually go down to 50 meters, 100 meters, whatever you want when it's in the flow. And here are some pictures here of the normalized center of mass versus drift. And normalized center of mass versus depth. So you can actually select your drift and your depth by just adjusting the center of mass location. I'm going to see now if I can play this other video here. This is a little bit longer. Here you can see this, the bottom ones here are the depth, and the top ones here are the, and this one I let run for several hours. This is kind of the interlude, so you don't see all hours of the simulation. And then here's at the end, you can see you actually have a situation where they're all at equilibrium and they're obviously separated by tens of meters. So you could actually, in theory, tether these 3 to the same buoy and get and have a working farm of these turbines. So this is what I think a great example of what dynamic modeling can do for you, because we didn't even know that this phenomenon existed before we started modeling them. So we started modeling these equilibria, and we started noticing that certain designs actually, instead of saying going dead center, that they actually started drifting to the left and the right and drifting down. And then we realized that we could actually exploit that to create farms of these turbines. So I think that kind of illustrates the power of multi-body dynamics simulations. Okay. So now I need to stop this and go back to the presentation. Okay. All right. Okay, so we did also some looking at, we wanted to look at sensitivity studies. These are some sensitivity studies to changes in flow speed. I'm going to skip through those just because in the interest of time. But basically the takeaway here is by tailoring the hydrodynamic influencing parameters that we discussed, we can actually set the turbine at a desired skew angle and also a given position or drift and depth. And so we think that this has great potential then for being able to create farms of these coaxial wind turbines. Next steps, we want to do testing of these turbine systems, see if we see this effect actually in the water tunnel. This will be done in Dr. Granlin's water tunnel. And then we also want to do some just basic kind of tether dynamics modeling in a fluid. We have a moving tether in a fluid with an end body. So we've actually built a water tank in the Engineering Mechanics and Space Systems lab. We have some high-speed cameras. We just got this operational about a week ago. This is you can see the system here. Here you can see the two primary students on this. This is Neil Ivankit, who's a master's student, and Chip Survey, who's an undergraduate. And let me see if I can get this video to play. This is actually a tether in a sphere, and this is moving in water. And you can see here, we have the high-speed cameras here, and you can see here that what we're going to do is, this is a system we can model because we have the tether in the sphere, and we know its characteristics. We can model what it should be doing in the water, and then we can compare that, and we can use that to validate some of these tether dynamics models that we've been using for this renewable energy. Okay, so just to kind of conclude here, I just want to kind of show, we've been in space, in the atmosphere, on the ground, and in the sea, and just want to kind of emphasize that it's really interesting that this project came along, because we actually had a lot of expertise in the lab because of all this other work that had been going on. So we often would doing this work, we'd often refer to master's and PhD theses that had been done for these other projects. And also some of the students working on these are actually working on these while this is going on. So there's an enormous amount of interchange of ideas between the students working on these various projects. So I want to thank all the hardworking students of the Engineering Mechanics and Space Systems Lab. Without their work, obviously this presentation would never happened. They also did a lot of work in helping me put the slides together. So I really appreciate everybody's effort on this. And with that, I think I'll conclude and see if we have any questions. I'll try and answer them.
Thank you, Andre. Appreciate it. Really, a lot of details in all kinds of applications. So to kick it off, I'll ask a question and then I'll let it open one.
Okay.
You alluded to this at the beginning. You go from space all the way to water. You have a different medium in each case, right?
Right.
So in the space, of course, the density of the medium is almost zero. Here,
exactly.
Water density is very high compared to air, and at lower atmosphere versus higher atmosphere.
Yeah.
So how do you take care of?
Yeah, that's a great question. So what we did, let me go back to this picture here. So what I guess what I left out of the proposal is that when we took the tether model from space to air, the majority of the work we had to do was to figure out how do we model the interaction of the tether with the atmosphere. And so what we did was what you do is you can do models. So once you've broken your tether up into the bead model, you have those different segments of tether. Each one of those segments of tether is model of the cylinder. So then we looked at aerodynamic, aerodynamic modeling of flow past the cylinder. So basically, okay, we created aerodynamic models, and then of course that model, all the work we did for that, then transferred directly to the ocean project, because what we basically then was change the density from the density of air to the density of water. One of the things we're looking at, yeah.
Basically, create a drag coefficient like CD for each.
That's exactly right. And the other thing we have to be worried about a lot is vortex induced vibrations. So I didn't mention that, but one of the areas that Joey is working on in the coaxial turbine system there is vortex induced vibrations acting on the tether, because you've got basically a cylinder in a flow, so you're going to have vortex induced vibrations.
All right, so it's open to questions. If anybody wants to jump in and ask a question, feel free.
Hey, Dr. Mazzoleni, this is Rodney, your student.
Yeah.
I just want to say, fantastic presentation. It really highlighted all the work that's going on. And I just wanted to tack on to your last comment, which was obviously perfect, where we go from space to air. We have to add in drag coefficients, and we have to deal with the viscous effects of the fluid. And I also want to point out one of the things that we've been discussing very recently, and maybe because we're just recently discussing it is one of the reasons you've left it out. But when you go from air to water, now we have this additional effect called added mass, where we not only have the velocity dependent loads, but now we have acceleration dependent loads that we have to deal with. And that's been one of the major challenges. It's a problem that's well studied and solved for single bodies of fairly smooth geometric shapes. But once you go to something like a tether, where we tend to model it as a large multi-body system, the problem of dealing with added mass for that system hasn't really been well worked out, and so that's what we're working on now.
Yeah, so let me go back. So just based on Rodney's thing, I actually had about 10 slides on added mass in here that I took out because I realized we'd be here another hour and a half. But that's one of the reasons we want to do these experiments here, is because we have some added mass models for the tether. And that's one of the things we want to do with this experiment here is look at, because we found added mass models for tethers in the literature, but they only cover what's happening, the kind of the translational loads. They don't include the rotational loads, added mass loads acting on the tether. So thanks for bringing that up, Rodney, because I hadn't mentioned that going through in time, but this is a perfect time to bring that up. Yeah, so that was another one of the main challenges based on Srina's comment. What happens when you go from tethers in space to tethers in air to tethers in water? And one of the things you have to worry about, in addition to lift and drag, is added mass, because you actually have this tether, as opposed to when it's just kind of like a static tether in a wind field. It's actually moving around, so you do have accelerations of fluid, and therefore you have added mass terms.
Yeah, it makes sense because water is 1,000 times more dense, so it is added mass for sure.
Yeah, added mass is a huge thing, and we believe we've got that. We believe we have it handled, particularly for the turbines. We actually have it handled. What we're working on now is for the tether model, and that's the last piece of the puzzle that Rodney's working on for his thesis.
I mean, I don't want to hog the questions, but anybody else has any questions? Feel free. I think Fugo.
Oh, Andre, yeah, it seems to me you have a lot of activity going on. I have general questions.
Yeah.
What's in your mind about research in the last 2 years compared with the previous years?
The last 2 years has really been focused primarily on this renewable energy, because the thing I like about it too, it's very, very timely, because renewable energy it's only going to become more and more and more and more important for the world in general over the next decades, but also because it actually uses everything that we've been doing over here on the left-hand side. So it's almost kind of like all the work we've been doing over the last 10 years in this space arena. It's all directly applicable to this tether project. And say we've got 3 separate efforts going on now, kind of simultaneously now in this renewable energy. So the bulk of our focus is on this. We're still wrapping up and continuing some of these projects that we began before, but the lab, as tradition, has moved heavily in this direction because it actually involves all of these, all the kind of the skill sets and knowledge base that we had developed for these other projects.
Yeah, it feels like it's more complicated with going to water from space. Space looks like simpler from the dynamic side of it, especially in the participating medium is such a complicated one with waves and things like that, right?
Yeah, the challenge in space is that if you look at the equations of orbital dynamics, they can very quickly become chaotic because it's so highly nonlinear because of the 1 over r squared dependence on that. And so, and it also has a lot of numerical issues because you're trying to track the position of these satellites. You want them to change their position in the order of like tens of kilometers, and yet your satellite is moving over distances of hundreds or billions of kilometers. So it becomes a numerical conditioning problem. So there's a lot of numerical issues. But in terms of the physics, you're absolutely right. The physics of looking at this system here, for example, these water-based tether systems, the physics is actually much more complicated than in space.
Yeah, makes sense. Anybody else? One more question? One last question?
Yeah, I was wondering, how is the collision avoidance dealt with underwater?
Yeah, so that basically
How
comes
did you deal with the problem of something colliding with the element?
With colliding with what?
with the either the tether or the helixes.
Yeah, so the tether itself is you know, kind of at the end of the system, but you might want to extend a boom there or something, just to kind of keep the tether separated from it. One thing is, I said, these systems are made to be neutrally buoyant. So if the tether should be severed, they would just float to the surface. Yeah, so that would be as far as the tether issue. As far as colliding with each other, you know, that's the reason that we want to design these things so that when they're in flow, they naturally tend to divert from each other. So
yeah, we're thinking more of a submarine or a boat or some kind
Oh, I see what you're saying.
other vessel.
Yeah, I mean, that's an interesting question. You know, that's not one that we focused on, at least to develop the technology. Very good question. And obviously, in terms of a systems management, you know, if you're the manager of this problem, we would be one group working on that. We're working on the technology. There would be a whole other group of people that would be looking at, you know, collision avoidance with ships and submarines. And then there's a whole other issue which has to do with making sure that they don't harm, you know, marine life, whales and dolphins and seals and all the, you know, the big, you know, marine mammals that are out there. So there's when I go to conferences on this, you know, there's a lot of talks that just talk about, okay, how do we protect the animals in the environment from the system? Because you're trying to help the environment by, you know, creating renewable energy, but you don't want to then go ahead and hurt the environment at the same time. So your question's a really good one, and it's very important. But it's not one that we're really working directly on, but there are people working on that.
All right, in the interest of time, I want to thank Dr. Mazzoleni once more for this seminar and appreciate all the details he provided on various interesting topics that's going on in our department. So I'm pretty sure many of you can reach out to Dr. Mazzoleni if you have any specific questions. But like I said, he's in our department, so you can catch him anytime.
I'd be happy, just send you probably an email. I'll be happy to answer any questions, you know, the best I can.
All right, so thank you all. Thanks for attending the seminar, and keep looking out for the next seminar details. Dr. Grace keeps sending out this information. So thank you.
Yeah, thanks everybody.